Yeah.
And so if you actually knew this stuff, then you got it.
It's like the first two exams, I lost points, but like dead by like missing
Yeah, me too.
design, miss a UA. Like nothing I did was necessarily wrong. It was just like not gonna share things. And they added it.
I know,
Bro, it's like
he's like stricter than he should be.
Yeah,
acting on that.
I agree.
Because
Brutal.
like half-point deduction on that is like cool, except it's a 20-point test. That's like, that's a huge fortune, you know?
It is.
Excuse, sorry.
It's a lot.
Oh, thank you. Oh, yeah, cool. Sounds like somebody got an exam back.
Well, we're just, we're just discussing.
Dr. Grace?
We're just discussing Dr. Gray's exam grading style.
Oh, yeah.
I heard it's brutal.
It
is.
Is it brutal? Is it brutal while it's happening and at the end you're like, I got a B? I thought I had an F.
No,
But-
it's usually like, it went bad as
Okay, but the
expected.
physics grading's like, the grading scale for all the physics classes is like, and a 79 is like a B or something, yeah,
It's like
B
a
plus.
The 84 is an A minus.
Yeah.
Anybody want some
I
tea?
appreciate
Got a little bit
Yeah, I
of
do
tea right
appreciate it.
here.
It doesn't make me
Eric
feel
doesn't
bad. I
have
would get
a
like a 70 on an
Coke
exam.
bottle I could pour some in. Here, you guys figure it out, you split that.
What did I do wrong? And it's like nothing. I just totally forgot 7 negative signs, and that's 7 out of the 15 points.
Yeah, exactly.
Whoa, what's all that?
Looks like a book.
It does, it's a lot. I like the love part, then you have to read more. Since we're getting a late start today,
It's okay, you owed us 3 minutes, so.
it's true.
It's not a late start.
It's true, it's true. Can you just like maybe go through your toes, starting on your left pinky toe? Just feeling it. The meditation is just like noticing. So just take a minute and notice your left pinky toe. That's really hard to do. But what's even harder is the next toe. You feel that toe? And then move through each of the toes separately. Just noticing the sensation. And try not to fall back on your memory of what a toe is. So if someone were asking you, an alien comes down, you forgot what your toes look like. You're trying to base it purely on sensation. We'll move across to the next set. We're going to go through all 10 toes. I'm on my big toe right foot right now. Exactly. All right. Keep taking your time. Finish up your toes. Meditation is not a fancy thing. Meditation is just living and noticing living happening. Got this water, looking at this water from the top. So we can think of this as some sort of like a lake, and there's an output valve under the surface here. So water's getting filtered from somewhere we can't see, and it doesn't disturb the flow here. Coming through the tube, getting fed back in by a pump, and coming out right here. And these vectors just represent the surface velocity. So if I had a leaf, ooh, here's a green one, just for a leaf. If I had a leaf and I set it on this surface, the leaf got in the whole other picture. Put this little leaf here. It's going to flow with the current, so it kind of looks like it would go to the right and then maybe up, maybe catch an upward drift. No, so maybe, I don't know, something like that. Just imagine a leaf on the surface. Now I want to think about a slightly different problem. What if I were to have like a little toy boat here, and I were to move that toy boat in some sort of a weird pattern like this, just along a weird path. Let's call it C for the sake of it. And I might be curious how much work that required. Physics people, what's work besides just force times distance? Can anybody give us a good sense of what work is? My math friends are off the hook. We don't know anything. We don't know how to do real stuff. I'm not even sure work is real stuff. That's part of the problem I have with physics. Lots of weird shit that doesn't seem to be real anyway, but we pretend it is. What's work? Can somebody give us a nice synopsis?
How much effort you put into an object over a distance?
Yeah, that sounds pretty good. We can think of work as kind of the net effort it takes. If we think about the basic formula, the only word I understand in this is distance. That's the only one that seems to have any physical meaning to me. Force is just like how hard I'm pulling, and I'm pulling a certain amount. I'm putting a certain amount of pulling in for a particular distance. So we've got good old W equals force times distance. But this is assuming that you have a constant force along your path. So the force here is constant. And I am moving in a straight line. Only then, and D is the length. I put a vector here, but really we're just thinking of D being that length right there. In this very non-realistic situation, this is how we would compute the work. So by the end of the hour, we're going to be able to compute the work done to pull that boat, or the work required to pull that little boat across this, what's called a vector field. So that's kind of where I want to start today, talking about vector fields. And I'm super stoked because we got here. Yay, we got here. We got today, we got Monday, and we got next Wednesday. And whatever we can get done between now and then, that'll be good. I'm kind of actually almost hoping to stop lecturing on Monday, and then having Wednesday be, let's just start getting caught up on things that need to be made up and doing some of the skill check stuff. Does this all sound good to everybody? Cool. I ran into, does anybody know Dr. Basham? Neuroscience? Yeah, I ran into him today and I was like, what are you doing? He's like, I don't know, calling off next week. He said, I'm gonna go into class and ask my students, what do you guys wanna do? Do you even wanna meet next week? I think we all know how that's gonna go. So this is a 2D vector field, but we're gonna spend a lot of our time working in 3D vector fields. And let's just talk about what this could represent. So you don't even have to draw this, just imagine 3D space, and at every point in space there's an arrow representing something moving in a direction and a certain magnitude. Something being applied to a certain magnitude. So this would be the kind of thing that if we were doing fluid dynamics and we were imagining the air currents in the room, just like at a particular instant right now, where is this molecule of air headed and how fast? And I would assign a vector to it. So imagine the whole room filled with, it's just fuzzy in here with arrows, just representing all the complexities of the wind and the motion of the air. That's kind of, so this was kind of the same thing. This is a big part of fluid dynamics. Anybody taking that here? Do we even teach that here? You know, that's pretty intense stuff.
It's more engineering, we don't have any engineering.
We will though.
Yeah.
We will. That's right. Yeah. Yeah, fluid dynamics deals a lot with non-linear systems. And all our systems that we deal with essentially are going to be non-linear. Linear is predictable. Nice old straight lines. Life ain't linear. Life is non-linear in every sense of the word. This is continuous. I don't even think life is continuous, it just feels that way, but that's just me. So how do we do this mathematically? What we're gonna do is we're gonna have a function, capital F, and it's going to depend on coordinates. So I'm doing 3D here, but if you want to think of the 2D version, just pretend there's not a z there, and then we have 2D. Yeah? Or set z equal to 0, now then I'm back in the plane. So this is equal to a formula for the vector attached to point xyz. So it's got a little hat on it. This is a vector valued function. We haven't really dealt with that. I don't think so. We've had functions that eat vectors and put out things. I guess we have had vector valued functions, our curves and stuff like that. But this is a different beast. This is taking the entire space and assigning an arrow at it. So let's look at some examples. That's honestly the best way to do this. Let's do a nice simple example, e.g. I'm going to do 2D because drawing in 3D is evil. F of xy equals vector yx. Get multiple colors because we want multiple colors. I kind of love this stuff because I love the idea of thinking of this as a flow in the plane or a flow in space. What does that flow look like? So what we're going to do is just get a bit of an intuitive sense about this thing here. And we'll probably have to finish some of this up on Monday, but that's all good. Let's make a little chart. XY, F of XY. Once we see how a few go, we're going to be able to kind of fill the rest of this in. Some low-hanging fruit, 0, 0. This, look what this says, switch the points coordinates. So this just comes out as a vector. I'm going to use vector notation, 0, 0. That's no motion here. So right at the origin, if this represents velocity or flow of a particle, nothing is moving at the origin. So no motion at the origin, but only at the origin. The minute I get off the origin, one of these coordinates will be positive, no matter which way I move, and there will become motion away from there. So let's actually grab a few. Let's take a look at some of the cardinal points. So that's 1, 1, minus 1, minus 1. So at 1, 0, right here, the vector is 0, 1. And that means I've got a vector, unit vector, pointing straight up right there. And I'm going to do these guys in blue. So the point is here, and attached to that is this vector that points up. And then let's do this guy, so 0, 1 is a vector 1, 0. And that is a vector pointed directly to the right. And they both kind of have the same tip, even though I did a bad job with my units. Could you go ahead and just finish up the rest of this real quick? Because it's so easy to watch me. Yes? Yes, sir.
F of XY or F of Y.
This is fxy. Yeah, thanks, Alex. I should put the formula. It's y comma x. Thank you.
Oh, okay.
Does that make sense?
Yeah, I see.
Okay, cool. Yeah, I should have put that up there. Let's just finish it up. Let's get the rest of those vectors in there. He's a little weak today.
I still like it.
You like it? It's got a little flavor. Looking good? Everybody kind of get how to do these? So it's simple, kind of satisfying. Let's grab a few more. Let's actually try to do some smart thinking. What happens if I have, bless you, what happens if I have an input and they're both, let's just say R comma R. So in other words, I'm on this diagonal. Because it looks like that diagonal has something special. What comes out? R comma R. Yeah, but as a vector. So for example, at the point 1, 1, right here, I've got the vector 1, 1, and that is keeping me on this diagonal. If I'm at the point 1/2, 1/2, I've got the vector 1/2, 1/2. So that means I go over a half, up a half, and it looks like that. And then every vector along the way is going to have something similar. So let's say we were at 1/4, 1/4. Got a little vector that does that. Let's look down here. If I have a -1, -1, so if I'm right here, my vector is -1, -1, so it points that way. If I'm at -1/2, -1/2, like so. So that line, that diagonal line looks pretty special because it means that if I put my leaf on that line, it flows on that line. So this is called, it's just like a word that's very fancy. I'm just gonna put it up here. This line, the line y equals x is, I'm gonna write this word here, stable, first, and that doesn't quite make sense yet, but it is true. Stable manifold. Manifold is a great math word. Manifold. Yeah, not like, yeah. Yeah, not like an intake manifold. And it kind of just means like a curve or a surface or something like that. There's a much more fancy technical meaning. But why is it called stable? Well, let's grab a few more points and figure it out. And I think now you might see that we can move faster. If I'm at 2, 0, then my vector is 0, 2. If I'm at 2, 1, so at 2, 1, now things might get a little weirder. At 2, 1, that vector is 1, 2. So at 2, 1, that means I move over 1 and up 2. So it's a vector that kind of goes like that. Now make sure you see that. So it's just 1 over, 2 up. It's got a slope of 2. That might not be precise, but it's close. If I went to the point 0, 2, that is the vector 2, 0. So that actually points straight across like this. What if I went to the point 1, 2? Then that's the vector 2, 1. And that means I go over 2 and up 1. That's actually kind of the flip of this guy right here. And if I kept doing this, and I'm not going to pedantically go through every point because you'll just want to leave. But if I were to look at the flow here, what I would see is that all the vectors, at least in these quadrants, are pointing toward that diagonal line. So when I call that thing stable, what do I mean? I mean that if I'm traveling on this and some noise enters the system and I end up off of it, I'm brought back to it. Do you see that? If you were trying to travel on this line and then an extra force came in and like blew you off course, the current brings you back to where you were. So that's stability. Stability is, God, I feel like I've done this in here before. I'm gonna do it again. Did I do that? Was that Calc 2? This is stable. That's a stable equilibrium. I'm at equilibrium, perturb it, returns. This is unstable equilibrium. Perturb off of that, you ain't coming back, ever. So that's the kind of stability I'm talking about there. And in the end, that word isn't gonna play much of a role for us. What do you think's happening in these sides? Hey, take a minute. What's happening in these quadrants, 2 and 4? Can't tell without finding some arrows. Anybody already found some arrows? I thought as much. Let's find some arrows. Because honestly, off the top of my head, I have to check. I can't see it. It's in my notes, but I don't want to look. And really, once you get a few, you'll probably start to see the pattern. I guess I should do it blue. It's nice and consistent. Let's see, so 1, 2, and then I go. Wait, is that right? Over and up. Like that. Just looking at all. I feel like this diagonal might have some special properties, so I'm going to put a R, negative R here, see what happens. Then I get negative R out. It's all along that diagonal. So if you're at 1, negative 1, you go negative 1, 1. Wow, you're actually traveling. So this is also another manifold. Manifold just being a place that once you're on it, you stay on it. The unstable or stable is the precariousness of that manifold. Is that a stable manifold or an unstable manifold? What do we think? Unstable, absolutely. If we got enough, well, if we got an app out, which we could get, but that's such a pain in the ass here to get apps out. What you would see is that you're always kind of moving away from this line. So these vectors down in this plane, they're pushing you toward that original diagonal. But if you are on this diagonal, you will slowly cruise to the origin. You'll never get there, but you'll slowly get there. Think about how the vectors here just get tinier and tinier as you move in. So you slow down. You're like decelerating forever. And you never quite make it to 0, but you get damn close. So this is an unstable manifold because if I veer off of it even the slightest, it actually takes me to that other manifold. And I travel over there. This all kind of making some sense? So just imagine the plane is filled with arrows, that's the current, and we can study that behavior. Now in a little bit, we can then ask ourselves how much work would be done if we traveled in a circle around the origin. How much work gets done total traveling around that circle? And to me, that's not obvious at all, but I don't even know what work is, so, yes, sir. Oh, okay, cool, okay. All right, let's try another one. I would like you to determine the flow. So please discern the following flow. This is a great way to end the semester. This stuff's so freaking cool. So, f of xy equals, I'm gonna make it kind of the same, but tweak. Yes, sir.
So could it still be considered a stable manifold if you'd be able to blow it in a direction where it follows another line and never goes back?
So, but it would never return to the original path in here, because these guys are all kind of, the forces are all pulling away from that guy they're telling. And what happens is if you veer off of this, you never return to it. You don't get closer, you only get further.
Well, I mean, like, if you were on the stable.
This guy here?
Yeah,
Okay.
you get like pushed off. We're now on the unstable. Aren't you like no longer gonna return to the stable again?
Well, it depends on it depends on how far you get knocked off. So for stability, think tiny perturbations.
Okay,
So like maybe think error.
okay.
Does that make
Yeah,
sense?
okay,
Yeah, that's a great question. Yeah, yes, if I'm here and I got knocked off sufficiently, then
Okay.
like I'm in a whole other show. Yeah, great point. Tell me about this flow. Get some flow, get some arrow. What's happening in the plane? You're gonna like this one, I guess. As much as you can like anything in here. Good to have you back. I don't have to harass you on the video now. It saves me a lot of energy. I can harass you in class, this is like first hand. Yes, sir. Of whatever we're modeling. So in general, yeah, it could be lots of things. The interpretation can vary from one thing to the next. Yeah, exactly. But like a good way to always think about it is it's just a current. Just a current, yeah. And the way I approached this was kind of the way I think you should. Get some low-hanging fruit on the coordinate. Understand what the coordinate axes are doing. Then look at the diagonals. And then grab some points in between to see what the interim behavior is between those things. This is gonna start looking like some Elon Musk if we're not careful with this thing. Definitely need more vectors on there. Elon coming in. once you get a sense, use your mathy intuition. You're good at recognizing patterns. I'm pretty dang positive on the things I'm seeing here. Get these halvesies here. The scale and stuff might not be. We're looking for the general feel. Are you feeling rotation happening? Some sort of vortex kind of behavior? Alexander, what can I help you with?
I don't know.
Is yours not looking like this? Let's take a look. Let me take a look here. Get a good sense of it.
That was looking good. Oh, okay, so let's see, are these your points here? So you got, so 1, 0, there, you went down, so 0, 1 is supposed to be that, yeah. And then at 0, 1, you got -1. 0, let's check this, 1, 0. Check the rule. Yeah, so this looks good. That's just +1. Yeah, because look at the rule, it says flip the coordinates and then just negate that second coordinate. I mean, since it's 0, it doesn't show up. So that's this is the y. So over here, and maybe put right up here. There you go. Cool, like that. So, yeah.
Oh, that's what
Mhm. Yeah. Good stuff. They're great points to use, so you did great there. So 1, 1, show me 1, 1, the point, just the point, 1, 1, right there, and then what are we doing? Going over 1 and down. So kind of headed to that too. Yeah, just like that. There you go, see? Got it? Yeah, check out the rest of yours.
Everybody feeling okay here? The sad thing is I worry about the government scrubbing YouTube, looking for people mentioning the golden inner circle. Little light just lit up on one of those dorks consoles in the White House. Somebody mentioned Elon. But I totally support the government. If anybody asks, all aboard. So what we see here, what happens at 0, 0 actually? Just 0. So the only place where if you start there, you stay there, is at the origin on this. Everywhere else, you would have paths for your leaves that were circles, and these vectors would become the tangent vectors to those particular trajectories that would arise in there.
Could you say then that like any like circle centered at 0 is a manifold for the vector field?
Yeah, I guess it is. Yes, those are manifolds. Yes, sir. Yeah, absolutely. And I don't know about, well, I guess they're stability. Yeah, I don't know what to
You
say.
kind of like move between circles and it wouldn't really.
Yeah, you fall off. You're just on a new orbit.
Yeah.
Yeah, you never get back home. That's for sure.
Yeah.
Definitely. But you're close. You can wave to home.
Totally,
As you
yeah.
every time, every year as you pass by. Can answer any questions on this. Yeah. I want to go back to that very. Actually, no. I got one more for you. I love that problem, I love the first one, and I've spent just way too much time in my life drawing these freaking vector fields because they don't have to be fancy to be interesting. So we've seen yx, we've seen y negative x. Let's just do something really simple. Sorry here, okay. Let's just do something super chill. And what I'd like you to do is get another sense of this one. And then this one we're gonna take a little deeper. So 2x, 2y. What's that flow? This one's every one of these is qualitatively different than the last. See if you, after you get a sense of it, are there any manifolds here? I wouldn't worry so much about getting the magnitude precise. We're mostly interested in the qualitative aspects of this. What does the flow feel like, not what precisely is that flow. The axes, yeah, definitely. But also, yeah, exactly, yeah. Infinitely many. For this one, we've got infinitely many straight line trajectories. Once you're on, check out how they're all oriented in the same direction. So once you're on one, you stay on one. But they're all straight lines. It's like, that was kind of like the very first thing I drew, where there's a source in the center here. So there's a source putting energy into the system right at the origin, doing something at the origin, like a white hole or something like that. I don't know, something cool and cosmic. Or just a sump pump, or something a little more banal. How do we feel about this trajectory? We good? Anybody need help getting this? Do you remember what this stands for? What's that stand for? Gradient. how do I find the gradient in 2D? Let's say I had 2D. What is the gradient? Yeah, beautiful. So it's that guy. Is that, hopefully that's like not the first time you've seen it. I can tell you it's not the first time you've seen it, whether or not you remember that. So this comes from some function. And what I want to notice here, want you to notice here is that if I have f of xy equals x squared plus y squared, that is the gradient. So the gradient of this thing is literally the vector field we were given. This is called the potential of the vector field. Does that make sense? Like physics, chemistry people, have you heard that term before? So this is the potential of the vector field. And what it represents is an energy state. So it represents like the total energy. And let's actually look at something really interesting here. If I take this down and I set it equal, so this is a function of two variables we could think of, there's an output. Let's look at the level curves. So what are the level curves? What are they? Christian, what are they?
Concentric circle.
Concentric circles. So the level curves, the places where the energy is constant, look like this. And of course we need C to be greater than or equal to 0 here, but we just get these concentric circles. How does the vector field relate to these concentric circles? Well, it's orthogonal. Exactly, yeah, beautiful word. Thank you. So the vector field is completely orthogonal to the level curves of this beast. But what this means is that if you stayed along one of these trajectories, it requires the same amount of energy to stay on there. It requires a constant amount of energy to stay on here. Whereas if you shift, this would be C is smaller, so there's less energy, less energy, less energy, more energy required as I move out. And think about why that would be, because the forces are stronger as we move away, and the forces diminish as we head toward the origin. So this is a cool little physics story. Christian.
So is like that shape like x squared plus y squared in like the 3D plane, that's like a paraboloid, right?
Yes, it is.
And it opens upward.
Yeah.
So how do you kind of like, I guess like rationalize that with like the fact that like the vector field associated is like also moving outward from the center, like instead of like bringing everything inward, kind of with the idea that like if you were like gonna drop like a marble into like the paraboloid, like why is it like moving to the center instead of like moving outward?
That's, I don't know if we can think of this, that the energy here is equivalent to having a little thing rolling inside you necessarily.
Okay.
I think that when we think about that, we actually have to think about the negative of the potential.
Okay. Is it more so like energy that would need to be exhibited to move from that point?
Yeah.
Okay.
Yeah, that sounds pretty good. So in general, the potential function you would think of as the negative of the thing that we just found. And when you look at it that way, that actually makes a lot of sense, right? Because at the peak, you would just roll off and you're constantly moving away from the center.
Totally.
But if I had negatives here and here, then this would be, then I would see that ball rolling toward the center, and that vector field would have all these reversed.
Yeah.
So yeah, there is an absolute relation to that. Yes. Yes, sir.
Actually, in physics, the potential, the gradient potential energy field is always negative to equal the actual force.
Oh.
So it is just flipped. The potential energy field is negative.
Thank God. Thank God I didn't lie. Because it felt like I was just pulling that out of my ass.
I mean, I've only seen it once or twice so
great. No,
far.
that's 100% right. You're 100% right. We're
You
not
said it confidently enough that like I wouldn't have been able to tell.
Half of just everything in life is just sounding like you know what's going
I
on.
don't know.
That's why sometimes being a professor is exhausting, because sometimes you don't know if you do. Especially in those seminars where I gotta run a discussion, it's a little scary. Here I kinda know what's gonna happen. I didn't know you were gonna ask that question, so that's good.
Keeping me on my toes.
Of course.
But I'm ready with confident bullshit.
Fair enough.
Which turned out to not be bullshit at all, so thank God. I thought I knew that from somewhere. All right. So let's talk about forces again. I want to go back to that work equation. So work, when we're in one dimension, the force required, the work done by exerting a force F, a constant force F over a straight distance D is given by this formula. If I go to n dimensions, the formula still looks the same. It's really beautiful. We have a work output that is a constant, that's a scalar quantity. It's a number that measures effort, like Daniel told us a little bit earlier, and it's equal to the force vector dotted with a distance vector. So it's the same idea. It's just that I've got this F that is some sort of force field in here, and the D is how far I'm traveling in that force field. So this is distance vector. So again, it's a straight line. That's just a straight line. D looks like that, and then this is some force. So let's actually draw this picture at a point. I'm in this vector field somewhere, and I've got a force acting like that on this particular location. And I'm not going to put coordinates here because I want this to represent one dimension, two dimensions, with n dimensions. And from this point, I'm going to move with that force acting constantly on me in this direction for that long. So think about that force acting constantly all the way along here as I move. And the work done is then given by this. And keep in mind, that is the dot product, which looks so beautifully like that. And in fact, multiplication in one dimension is the dot product. You just only got one component. So they're the same thing. The dot product is a beautiful generalization of multiplication. Well, that's all good, but we know a little bit more here. We also know that this is equal to the magnitude of F times the magnitude of the distance times the cosine of theta. What's theta represent? The angle between them. Yeah, exactly. So let's take a look here at this. This quantity, when is it maximized? Say that way. So angle 0. So let's think about cosine. That's the key.
Yeah.
Does that make sense?
That does make sense.
Yeah. So let's think about a cos theta, and that you spit out a 1 when you have theta is 0. And then you actually get just the magnitude of the forces. This is when they're acting in the same direction. So here, there's F, and then here's D. They are acting in the same direction. As this direction that I want to move in this field starts to veer away from here, the magnitude decreases. So the work done becomes less, or the work required becomes less. That doesn't even make sense. What the hell is work? Because
Force times the distance.
yeah, it's force times distance. That's about as good as I can do. Because I'm thinking, like, it's maximized when these two are moving, but that actually seems like that's the easiest, right? When I move with the force.
That makes sense.
Because
It
you're doing
does
like
make
the
sense.
most work, like the product is like the most.
Yeah,
Because I feel like
You have like a marker that could be harder.
it does. Yeah. Yeah, it seems like the hardest would be when I pull in the opposite direction.
Are you thinking about it like as an energy expenditure though, like energy lost in doing something?
That'll
I
sound
also
way more
don't know. I don't really
sophisticated
know
than anything
physics.
I got in my head.
Well, energy is the ability to do work, if that makes sense.
Ooh, what's that?
Energy is the ability to do work.
Energy is the ability to do work.
So yeah, it's remote.
What is work?
Great question.
We need to find out. I need to, like, if somebody could come in next Monday and give us a cogent, sane definition of work.
I was like,
I don't know what that is.
It's like asking for torque, you said force across the radius.
Yeah, exactly.
I don't know how else to describe it.
That's how I've done physics my whole life with formulas. It's gotten me pretty far. It's just the explaining. When is this 0? Yep, 90 degrees, exactly. Cosine is when you have cosine of pi over 2. So this is going to equal 0 when we are acting orthogonally, or moving orthogonally to the force field. And then it's going to be at its most negative when they're acting opposite each other. And that's just going to have a negative sign in front. And that's when D acts opposite force. What the hell is negative work? Work
Going
owed,
the other way.
back pay, like overtime. I don't know what it is. Like,
It's like in vector form, which is the opposite direction.
yeah, I guess it's just directional. Yeah, that sounds pretty good. Maybe I'm thinking too hard about it. That's the problem. I got stuck in mass a long time ago. I don't really understand mass. And I know nobody understands gravity. Just some of the fundamental things to do the simplest computations. All right, but what we want to do, we don't want freaking straight lines. We want cool paths that look like this. Well, look better than that. Kind of like that. So I've got a curve in space. And it's moving through a vector field. F. So there's forces acting all along here, and I'm kind of just moving on my own, independent of the vector field, but things are battering me, right? Things are pulling me in different directions depending on where I'm at here. So how do we find the total work done in moving from here? Let's orient this thing. And let's actually put the word oriented right above here, an oriented curve in space. How to find total work done moving from A to B. And A is this point, B is this point. It's got a funky, cool curve. How does the work differ if I were to do that, and maybe some weird polygonal curve? So I've got C2 here, let's call that C1. There's curve 1 and curve 2. And what if I just travel directly across there, C3? How does the work change when I do that? Now what we're gonna find out is it's the same amount of work no matter what we do. No matter how we travel. That's a result we're gonna see, but not until Monday. Which makes work mean even less to me. Completely even less to me. Yeah, I'll stop by and chat with him before class on Monday.
Might be a bit of a conversation.
Might be what?
Might be a long conversation.
Might be. But I like talking to Dr. Gray about physics.
Yeah, that's fun.
He is fun to talk to. I don't have to take his exams, so there's like zero stress there involved. Actually, before we do that, let's practice a basic skill. I want to make sure our parameterization skills are in place. So let's just warm up. Would you please parameterize the line segment between counts. 0, 1, minus 2, and 3, minus 1, 2. And I just want the line segment between them. Okay, cool. Take care. Thank you. And I want it oriented, so this is actually an orientation. We're gonna start at this point, and we're gonna end at that point. It's a bit of a challenge. That's just, it's been a while. Do you want me to put up a quick outline of how to do this? Yeah. Been a while. Those can be in any dimension. Step one is to get that direction vector. Step two is use formula. Let's see, so I'm gonna have, let's see, so we need a point. We start at P naught, that's our anchor, or P1. So our P1 plus T V. That's about it. Pretty straightforward, but it's been a while. So again, that procedure is find your direction vector, find the difference. This, make sure you do where you're headed minus where you come from. Otherwise your orientation will be backwards with this formula. And then this is the first point, whatever that is, you're based here, plus you, that's your parameter t times that vector, and you want t to run from 0 to 1. Just want to check some things here. Notice that r of 0 is P1, and r of 1, when t is 1, you get P1 plus this vector, which is P2 minus P1. That just gives you P2 at time 1. Good thing to have handy. You're going to be doing that, I promise. So doing that together, let's see here. So I'm going to have r of t equals, so it's kind of, let's see, P1. I guess I should put a little vector hat on him, pretend like he's a vector now. Plus t times the difference of those two. 3 minus 2 fourths. Does that sound right? Sanity check for me. Thank you. Cool. And then always give that range. You always want to know the range of your parameter. Cool. So let's call that C. That's curve C. How would you? And I want you to think about this for a minute. If I give you a certain curve, and I say that curve is C and it's got a orientation to it, then minus that curve is just traveling in the opposite direction. What is the parameterization of minus C? So take a minute and see if you can, it's more than a simple tweak. You can't just replace T with minus T. So what is the minus C? parameterization. And you could do it from scratch, of course. There's nothing wrong with that, you know, just reverse. I'll show you a couple ways to do it. Just curious what you might come up with.
Is that minus?
Yes, sir. That was nice. Yeah, just traveling this guy backwards. Anybody got something?
Maybe flip the signs of V
Flip the sign of V.
and then use P2 as P1.
Yeah, that would be an easy way to do it, definitely. Did y'all see what Daniel's suggesting there? Take the vector V and just flip its sign. So take the negative of it, which would be P1 minus P2. So here we could use V equals minus our old direction vector, because we're traveling in the exact opposite direction. Like so. And then what did you say? And then adjust this point here and start at this guy instead. So here we could have R2, let's call that R1. R2 of t is equal to, start here, so 3, -1, 2, plus t times our reverse direction. And then that'll work pretty good. Did anybody do it differently? There's one other way I can think of to do it. I'll show you the other way. Or, let's see if these are the same. I think this is right. Take the original, and instead of using t here, replace that with 1 minus t. So when t is 0, you're at the output of 1. When t is 1, you're at an output of 0. So it actually travels the parameter space backwards. Let's see if that works. So plus 1 minus t, and I'm going back to original dude right here. 3 minus 2, 4. And I think actually if you work it through, you're gonna get exactly, if you simplified this and reorganized it, we'd have exactly this guy here too. So here's a little rule of thumb. Given this curve C, which looks like this, given by R of t, and the parameter space goes from A to B. Boy, it sure would be nice as 0 to 1. I want to travel that backwards. So I'm thinking, I guess B minus, yeah, just let's not get, I'm just having too much fun here. Okay, I'll stop. I'll think of it over the weekend. Take each situation on its own. So that's minus C. Let's see, I want to do, also, one thing I want to point out, these parameterizations are not unique. You could have infinitely many parameterizations. So for example, I could put a 2 here and then a 1/2 here. Notice that gets me to the same place. What's different? It's faster. So this is kind of getting me there a little bit faster. It's speedier. Your time takes half as long to travel as it would have in the original parameterization. So parameterizations are not unique. And you generally want to go to the simplest one. All right, I got another one. Here's a challenge for you. I don't think we're going to actually get to that finding work stuff till Monday. And honestly, I think Monday's going to be the last day I tell you anything. that you're responsible for. I don't know what's, just like in real analysis, I don't know what's gonna happen on Wednesday. I might wanna tell you crazy shit. We might just like, just have work day or something, or sit in my office, you come visit me, or something like that, we'll see. So here's what I'd like you to parameterize, please. Let's see what you remember of this. Parameterize a circle of radius 3 centered at the origin, and so 0, 0, we're in a planar situation here, starting at 0, -3 and ending at 0, 3. So let's draw the picture. Always get your picture out. So we're going to start down here. And I think I need to tell you what direction we're traveling as well. Let's go clockwise. Yeah. Well, does that still, I think we still have a little bit of a problem here, or don't we? Let's see. Is that well defined? Because I could travel, I do need to say clockwise. Yes, okay, got it. Clockwise travel. Because there's 2 ways to get from one to the other. So give that some thought. Give that a little effort. See what you remember, or look it up, or what have you. But you know cosines and sines are going to be involved. Think about how we parameterize the unit circle. We did that a number of times. We'll probably actually meet on Wednesday. I'm not going to be a total lazy ass. I really want to be. What's that?
We've been talking about Wednesday for like.
There's infinitely many ways to knock this out. None of us might have the same parameterization. You got something, Othman? No. Oh, okay. Okay. Put up some things that you can use to think about. They aren't really the answer. What does this do? Where does this start? What point? What's cosine of 0? 1. Sine is 0, 0, so it starts there. Which direction does it move? Clockwise or counterclockwise? I think, well, so the best thing to do is grab the next parameter value, right? And just check. So grab a nice old pi over 2. Cosine of pi over 2 is what? 0. Sine of pi over 2? 1. So moved up to there. So moving counterclockwise. You see how I did that? Just grab a couple sequential parameter values and figure it out. So that's the whole thing there. How would I make that circle of radius 3? Put a 3 in front. Yeah? Put a 3 in front. And now it's a circle of radius 3, and I'll just change that label. That's easy. Scaled instantly. Beautiful. How would I make it travel? So that actually, that's not the right direction for us, is it? How can I travel in the other direction?
You just put your 0 and 2 pi for t.
Well, we wanna have our parameter space, I like that idea, but we wanna always go from lesser to more.
Oh, yeah.
So we gotta be careful with that. We could do 2 pi minus t. I think that would work. We could replace t with 2 pi minus t. But we could also do a different trick.
Just switch the sine and cosine.
Ooh, let's try that, I like that. Let's switch the sine and cosine. So let's try 3 sine of t, 3 cosine of t. Where does that start? So when t equals 0, where are we at? Well, it's a vector, right? So when t equals 0, what vector do I have? Or point? 0, 1. So 0, 3 if I'm going to keep my 3 boy up there, but yeah, 0, 1. So that would start me up here. And then let's see where we'd go. T of pi over 2 is going to be where? Yep, 3, 0. So that is going to be here. So yeah, so good job, Brandon. That's definitely getting us rotating in the right direction. Now, there's so many ways to attack this. What's the simplest way? So this looks good. This will be our parameterization. What could I do to the parameter space to just make this so simple? So 0 to pi. So 0 to pi, that's close. 0 to pi is going to be this piece though, right? It's that first half. Christian, you're making a face.
I think I'm just confused.
It's okay. So when t equals 0, this guy's at 0, 3, so up at the top.
Yeah.
And then when t is pi over 2, I'm at 3, 0. So that's here.
Okay.
And then when t is pi, I'm definitely at the bottom. But that's the right half that I would be moving through if I went from 0 to pi. That's the right half.
Okay.
But we want,
Oh, okay.
that's what's
Okay,
confusing you. So what do I do? Yep. Pi to 2 pi. Just grab the second half. Nothing magical about 0. So we could just say, let's let t start at pi and run to 2 pi. And we're good to go. Yes, sir.
For changing your direction, would it have worked to done -3 cosine, -3 sine?
I think so. Let's try.
If you did that, would you then be able to? I think you would be able to use 0 to pi.
I think
as, like,
so.
a parameter
Let's try it.
space, so that'd be
Yeah,
easy.
yeah. So let's just see really quick. Gosh, I owe you more money. I need time. I'm not paying you. I got no money. I'll send you 100 memdex.
No,
I'll send every one of you 100 memdex. Just give me your wallet address. So let's see, when t equals 0, we're at -3, 0. And then when t is pi, where are we at? We're at, well, let's do pi over 2 so we can tell direction. That is 0, -3. So let's see, so -3, 0, and then 0, -3. Yeah, I think that would work. So this also works. Yeah, good call. I think that also works. I think another way would be this. R of t equals 3 cosine of 2 pi minus t, 3 sine of 2 pi minus t as well. I think that also works. Maybe. I might be wrong. Anyway, it's fine. Let's call it a day. Thanks, everybody. Dan, are you gonna be back next week? Yeah. Okay, good. Do you actually